All right. Oh yeah, that definitely works. Hi everyone, thanks for coming to Causal Islands. And as Ishan just mentioned, I'm going to be talking about seamless services for an open world, talking about light cones, user agency, and connecting absolutely everything. The past couple decades, really, the incentives in tech have been to gather as many users as you can, build a wall around them, and defend it with a moat. And there is connections between these different little fiefdoms, but they're only really done point to point and in a very closed world model. For us to make any further progress, we might need to think about doing things differently. In fact, this is not a new idea. This is a fairly old idea, right? Even the late, great Joe Armstrong saying, wouldn't it be great if we could connect every process to every other process in the world? To talk about this utopian vision, I'm Brooklyn Zelenka. You can find me anywhere on the internet as Xpeed. And I'm the co-founder and CTO at Fission, where we're working on tools and technologies and research to do exactly these things. My background is mostly in programming language theory, virtual machines, and distributed systems. And increasingly, I work on standards and less code. Zishan has written the bulk of the code that I'm going to be presenting near the end. But if you're into standards, we're actually going to touch on a fair number of these as well today. So if nothing changes, the rolling weight of the status quo looks something like this. If you want infrastructure, you need to go to one of them, or maybe this long tail as well. But really, it's Amazon, Microsoft, and Google, sometimes called the hyperclouds, that control most infrastructure in the world. And they do a pretty great job of doing things at scale, but just Amazon alone has as much of the market as that entire gray section, right? If we don't want this trend to continue forever, and on one hand, there's nothing wrong with that. They're really great at scale, but I'm not sure that I want Amazon to own absolutely everything on the internet and all of the infrastructure and decide what goes on and off the internet. So if we don't want this to be the case, we need to take the current light cone of the future of all possibilities and redirect it, at least a little bit, just tip it off its axis so that that no longer becomes the default position. What we're talking about today is nothing less than connecting all of the world's users and services using open interoperable standards. We've already done this before. We have TCP and IP and HTTP. Nobody controls HTTP, right? There's a standard, anybody can implement it. It runs on every machine worldwide. We can do this again. But we need to do it now for storage and for compute. And anything that we come up with has to be substantially better than the status quo, right? It can't just be because it's decentralized or because it has user agency. People say that they care about these things, but then they also, Facebook has 2 billion users. It has to be better both at the level of the future that we want to see, but also to make it convenient enough for people to actually adopt. When we started looking at these problems, not quite 4 years ago, we knew that we always wanted to get to compute. And to do compute, you have to have data. And in order to do data in production, you need to have an auth system. You can't just throw data out into the world, especially when it's available absolutely everywhere. People often like to put auth above data, but it's actually more fundamental. It's not like someone put us on this path intentionally, right? This was all done with similar ideals to what we have today and what I'm presenting today. It was all these small, reasonable steps that got us into this painted back corner. A lot of the web was designed in the 90s. Back in those days, you had a beige box under your desk. It was relatively slow, and you had to dial into it and tie up your phone line. So, of course, you would rent a box somewhere else, and you'd put they would run a process in front of it with, more professional hardware, and you'd connect to it over the internet as you needed it. So maybe they're running a mail server for you. But you're not always connecting to it, so they can scale up and do multi-tenancy and have lots of people on the same machine, which means that they need to put access control so that we can't read each other's email inboxes, or we can't look at each other's photos, unless it's intentional. But of course, now the demand side has scaled up per provider, so the server also has to scale up too. So we do replication, we put load balancing in front of it, and we have this many-to-many system hidden behind this abstraction. And over time, that gets really difficult to work with, and we want to scale things automatically up and down, so we invent the cloud. 15 years ago, I worked as a Apple genius and was interacting with the public every day. And people would come in really terrified about the cloud. They didn't know where their stuff was anymore, right? This was a new scary abstraction that we now take for granted. And now we have these even scarier, newer abstractions like serverless, which is ironically more servers. And but at least it's finally breaking out of this same pattern of I, at least conceptually, have a computer running somewhere. At least now it's coming down to functions. And so this picture played out for many, many years. And fundamentally, we've been trying to keep the same picture going for a long time. We have this single source of truth, right? We have like the database, or where's the server? This has created front-end development, back-end development, DevOps as specialties that are deep, right? You want to learn Docker and Kubernetes and all of these parts. It is a multi-year endeavor. You can't just pick it up and go and start running. And we invented the LAMP stack in the late 90s to work in this beige box world, and we've been extending it since, right? We want to make the thing running in the cloud work like the thing that's running locally. And we've extended this metaphor for literally 20 years, 20 plus years, actually, at this point. We're taking this random walk through the solution space. And it's not like you get a zoomed out view like this. You're sort of in a dark room trying to find which way up. We're performing gradient descent on the future. We've hit a local maxima. I refuse to believe that what we currently have is the highest possible point in the design space. Just AI, zero-knowledge proofs, and fully homomorphic encryption have blown my mind in the past 5 years. Things I literally didn't think were possible. So there's no way that at the networking layer, we've hit the maximum possible solution. It's also possible to go deep, deep into a dystopia. We want to avoid that too. But even if we find the next hill, we don't know if that's the maximum one. So we need to go and explore a huge number of approaches, and we need to have technologies that let us explore all these approaches, that don't push us into a single funnel. So we want to find our way up here over time. Sometimes this means taking things like the LAMP stack or other tools and saying, well, what if we threw out the basic assumptions of it, took all those pieces and recombined them again, and see where else, with the new things that we've learned, we can create a new structure that's maybe more fits the ecological niche that we're in. Or another way of putting it, what if we burnt it down and rebuilt it? So we're in this new environment now. We no longer dial directly computer to computer. The network supports that, but we don't do it. If I want to send a photo from Winnipeg to Saskatoon, I first cross a border and I go to US West and make this loop, which at the level of sending a photo, nobody's going to notice, right? However, it is a tremendous amount of added time, energy, carbon, and just maintenance of all the plumbing, right? All the routers, all the fiber in between. As data starts to develop faster, and we start to have IoT and AI generating more and more data, right? Self-driving cars on Teslas, they have LiDAR arrays that are pulling in geospatial data, and it's so much, so large data that they can't actually push it over the pipes over your home Wi-Fi. It doesn't make sense. They do some pre-training on it locally on device, like literally in your car, and send more of like a snapshot of the data back to the main servers to do larger self-driving learning on. If we're producing data at this rate, we end up in the situation called data gravity, where the more data you have, the more you start pushing data or pushing jobs to that one place that produces more data, and you end up getting sucked into this black hole where the data can never move from there. And there's no actual solution to this problem, right? But we need to be able to work around it. when we look at cloud infrastructure, so these are, I'm going to pick a little bit on Amazon, mainly because they're the incumbent. Here's Amazon's servers worldwide, and the number of servers per region. And because Amazon's responding to the market forces of capitalism, they obviously make this really efficient, and they put it near large population centers, which means that they can invest in places where people actually are, because nobody lives here or here, except that they do. And the main difference is that these people aren't profitable. They're online, they're coming online at a very high rate, but it doesn't make sense for them to serve them, right? The data center in Cape Town is significantly more expensive to store data in than US East 2, which makes no sense, right? Except it makes complete economic sense because it costs them more to run a data center there, because the individual people there are less valuable to them. Just this circle has 50 million people in it. In North America, we have about that many people per data center. In South America, it's about 1 data center for every 500 million people. And in Africa, it's 1 for 1.5 billion. And there are parts of the world that don't even have a direct land connection. You have to put a wire underwater or go up to a satellite to do connection. This works okay, right? For you're sending a text message, it's not that critical. Even if everybody's sending stuff into US East 2, like, okay, fine, it's going to take an extra couple 100 milliseconds. It's fine. But increasingly, we have need for self-driving cars, IoT, geospatial data, and AI, et cetera, that need actually lower latency computing, right? Ericsson has set the line at 8 milliseconds for doing things like factory automation. 8 milliseconds with the speed of light is actually not that far, right? So here's 8 milliseconds in a vacuum. So this is the absolute physical ideal. Gets you not quite to Havana, gets you close, gets you off the coast of Florida. If you want to do that as a round trip, that gets you to about Halifax. And if we put that in ideal fiber, perfectly straight, no curvature, nothing, gets you about to Montreal. This means that as we produce this much data at these rates, increasingly, we get trapped in these causal islands. And yes, this is the slide where Boris named the conference for. Because data travels at maximum at the speed of light, we can't keep up with each other all the time. This is a light cone. We live at the present, which is the middle point there. And as a signal emits from that point, it extends out, sort of ripples out from that place. And we can finally get into points where there's some overlap, right? And often people at this stage say, oh, well, that's really great. I'll just put my data center between all the other data centers and have like a relay or some consistency check there. And this has been done. Google has a system that works basically like this. It's like it's okay for most things, most of the time, for point-to-point between data centers. The problem is, as soon as you start adding in other points, it gets really tricky really fast. Because essentially, you have multiple light cones sitting next to each other. And if we only work in this tiny little triangle, then we end up in this case called causal subjectivity, which Quinn will talk about a fair bit tomorrow with the Rhizome database work she's been doing. This idea that a server has to live in a specific place doesn't respect physics. This isn't an ideological point. This is base physics. We can't keep up with the amount of data that we're producing. We need to move our data and our compute closer to where users are. And for things that are trapped in data gravity, so the data itself, we need to be able to move the compute to the data, not always downloading the data and computing on it in a data center. Beyond that, unlike the 90s, we have a very varied network, right? We have extremely powerful devices in our pockets that can do most computation that they couldn't do 20 years ago. We have cloud and now edge servers, things that are much closer to users, and things that are starting to be run by the commons, by everyone, by you and me, right? IPFS, BitTorrent. This means that I can start something from the browser, have it kick off a WebAssembly process that calls into an edge worker that goes over into IPFS and grabs some data and operates on it. Right? It needs to move seamlessly between all of these different systems without having to go through the same auth server over and over again. In short, places are not a great way to organize computation. They're a way, they've worked pretty well for a while, but we've now grown beyond them. So how do we get back to our roots? How do we make the network good again? The good news is that this has all happened before, and I'm sure that it'll happen again. If you go back and look at the history of telecommunications, radio, telephone, we've ended up in a similar situation. And we've found solutions. And I'm sure that even with the things I'm talking about, we will find the difficult parts, the local maxima, that we need to then go and explore other places too. When the web was founded, it had these principles. So this is in the early 90s. Decentralization. I don't mean in the blockchain sense. I mean literally that the network is decentralized. The internet was designed to be resistant to nuclear attack, right? So you need to have things spread all over the place, which also means you need lots of providers running things. Non-discrimination. You can run any service you want on top of this network. Bottom-up design, universality, and consensus. Consensus, again, meaning that we're just going to agree on the standards that we run. We almost ended up in a situation where there was a Microsoft internet and an Apple internet and an AOL internet. And that didn't happen, thankfully, because we adhere to these principles. And in fact, we've done a really good job with these through the bottom layers of the stack, so at the physical and the data layers of the stack, not so much at the application layer. So a lot of this work that we're talking about is taking this and extending it all the way, finishing that vision from the beginning of the web. There's this idea from Simon Wardley that inventions start relatively visible and novel and slightly broken, and over time become a utility and become more mature and become invisible again. And that the structural system says that most of the money for this is going to be down at the far end of utility, when we're doing things at high industrial scale, which entrenches that position of, well, we're going to keep things the way that they are as long as they are. We're going to run the LAMP stack forever. But when you get down into utility and it becomes invisible, it opens up new opportunities for new innovation. And so you have people trying things and experimenting and starting this next cycle repeatedly. Distributed systems and concurrency have followed this path. We started really concerned about physical infrastructure. How do I actually run a disk? How do I move the needle on a spinning platter or a tape-to-tape reel to do concurrent processing and loading data concurrently? We moved into immaterial objects, basically abstractions over that, distributed state machines, and we're roughly here in this picture, right? We have some distribution, and we're starting to explore adversarial things, asynchrony, failure, et cetera. And a lot of this work, for especially the back half of this presentation, kind of moves that over and says, well, what if we worried about, yes, these trustless systems, but also in a scalable way? We need to do this in a way that respects user agency by default and out of the box. There's 4 principles, right? You need to be able to enter a system. You should have the option to leave without being held hostage with your data or your service locked into a particular way of doing things. You should have control over your own data. You should be safe no matter where you move on the internet. And you should be able to provide capacity to others. You should be able to plug in a desktop machine and have it serve compute jobs or serve data to others. So finally, in the past few years, we're seeing signs of a way out. And this is both technological and social. They're both algorithms and systems being set up, but also a social consciousness. You know, if you look at Mastodon or Blue Sky, right? People are becoming aware of these things. There's a movement towards self-certifying data. Web3 is a bit of a controversial term, right? A lot of people think that is just about blockchains, but there's another group that has sort of big tent Web3. And honestly, I don't really care what the term we use for this. If we want to call it the self-certifying web, great. It's just a bit of a mouthful, where we have cryptographic user keys to say, I did this thing, I'm going to write back. And content addressing, so the ability in, say, Git to say, yep, this is the hash of the thing, I agree that this is what was actually committed into the repo. And there's actually one layer around this, which is not just authentic data, but also authorized data. Proof that you were allowed to do that right in the first place. The way historically we've done access control in that auth data compute stack that I talked about right off the beginning is with access control lists. So here we have a user, and they want to access some service. And when they make that request, they get stopped by, essentially works like a bouncer in front of some hip, cool club who says, are you on the list? And you present your ID, and they go and they look at the list, and they say, yep, that's you, great, you're allowed through, and you can actually talk to the service. On one hand, this is great because you can put this thing anywhere in front of any service, and it'll work. The downside is that the user and the service aren't actually in control anymore. It's this auth service that's in control. And if anybody can take control of that, they can take control of the service, because now this is a trusted link. Additionally, this list is now the source of truth for who's allowed to actually do things in the system. So even if we wanted to interoperate with others, we wanted to have another service use this list, we either need to synchronize those or always make requests into this auth server continuously, which is in fact the situation where we found ourselves. The other solution for this, which is not a new idea, but that is starting to gain some steam, it's called capabilities. Here you have your user and some service, and the user knows how to find the service. And they send them, it's essentially like a ticket. So the metaphor, instead of being a bouncer, it's like when you go to the movies, you get a ticket, and they don't care what your ID is. They don't check who you are. They just say, do you have the ticket? Great, you're allowed in. And even better, if I can't go to the movies that day, I can give my ticket to Zishan, and Zishan can go instead. This puts me and the service in control. All of the required info is stateless, so it doesn't belong in a particular place. It can move around with requests directly. And this is where the movie theater metaphor breaks down a little bit. I can make copies of these tickets and tell others how to access this service without having to talk to a third party, without even having to talk to that service directly first and say, yeah, I gave them the ability to also call in. They're going to do this on my behalf. So I can send somebody else this little ticket, and they can also now make requests. ACLs and things like OAuth. This is a OAuth negotiation flow. It is, I think, 12 steps. This first half is negotiating with the authorization server, so the yellow box, the user, application, and auth server saying, okay, user, do you really want to give this application access? Yes, and it goes back and forth a bunch of times. And anything could fail in the middle here. And then once that's done, the resource server, the place where you're actually trying to run some compute or get some data, has to still go back through this authorization server and say, the thing that I got from them, is this valid? Am I allowed to actually do this thing? We've got to go back and forth a bunch of times here again. It would be really great to not have this single point of failure in the middle, this place where we always have to connect out to and go and pay the latency for. And so with capabilities, things like UCAN, there's a bunch of these system now, it simplifies the picture greatly. Right? Here's that first half. It's literally the application asks the user, can I do the thing? Yes, great. And then later, it can use that token that I got from the user to go to the resource server and say, hey, look, I'm allowed to do the thing the user says so. It's a much simpler picture, even in our heads. So that's auth. That's the bottom layer. What about data? Historically, we've used physical addressing, location addressing, and this is never going away, right? This is base bottom truth, right? But we want to get away from it as much as possible. In fact, we've already done, nobody types in, when you go to your browser, 42.123.45.6 to get to some server, right? We've added domain names. You go to example.com and you load whatever's over there. And it's just a mapping of a friendly human readable name to an IP address. It's a mapping of a name to a server. But it's still fundamentally about the location where something is. If I load that page tomorrow, it could be different. And to scale that up on, say, a CDN is really difficult, right? We need to do all kinds of tricks to fake that we're actually at example.com. There's this newer idea called content addressing, where we say, here's some content, and here's its hash. I'm going to run it through a function and get a small digest that's unique to that content. And I don't care who has it. Just find it for me. And so if I hash some data, or you hash some data, or a third-party provider hashes that data, we get the same value. It doesn't matter anymore where it lives. This also helps for linking data together. So I can have some JSON that has a hash of its own, and it can link to other chunks of JSON, producing a nice, rich graph. And once I resolve that first link, which we could even put behind a domain name as well, I can follow paths inside of here, just as easily as we would with normal pathing. So these are the starts of some open services, at least for auth and at least for data, right? These are ways that we can actually connect systems together. These exist today. They're a little bit early. They're getting adoption. They're moving forward a little bit at a time, right? People have been using things like magnet links and BitTorrent to download their Linux ISOs for a while, right? But we need the same thing for compute. So compute, like data, should be ubiquitous. It should be everywhere. We shouldn't have to think about it. We should be able to depend on the idea of having compute around at all times and only go out to the network when we actually need something. Not as the default, because that's where the compute lives, but because I can't do something locally. My phone is way more powerful than my first laptop, right? I can do 99% of things on device. And when I do need to go out, it's because I need to use a GPU or some other resource that I don't have locally. This needs to be fully consistent between clients because I need to be able to move compute from here to there and have it be equal. And ideally, I would like it to be deterministic so that both runs are the same. So they're completely indistinguishable. In the same way that we had content addressing for data, I want input addressing for compute. And we need to replace the hard dependency that we have today on the hyperclouds with open protocols and nodes. That's not to say that they're going to go away. They've done great things at scale, but they should be able to participate, and we should level the playing field for everyone. Developers don't want to think about compute. We hear this over and over again. They say, well, I just want to write some code and just have it taken care of. And this is what serverless was sold as, but hasn't really panned out because you have to go to these specific proprietary APIs that are different based on the provider. And people are trying to abstract over them. And maybe if you write it like this, then you can run it on both Azure and Lambda. But you need to tweak it like this because sometimes it'll be on Azure. Like all of these things, it gets really difficult. With open standards, we can make this picture really easy. We have users and devices. We have service providers. And they can just dip down into the ubiquitous compute substrate and pull out values, regardless of where they are or on what device they're running. It also means that if you have a request that has multiple components in it, you can route that anywhere around in the network and say, OK, I want these 5 things run. Cool, I'm going to send that out to some compute broker, and they're going to pass that along to who can actually run these tasks. And let that sift through the network until it can find the relevant service providers. What this enables in addition, when we're talking about the potential solution space, is truly disorderly programming, where it doesn't matter where you're going, right? We should make it so simple to think about compute that we can experiment with different ways of computing and different different kinds of services without having to say in advance, like, well, I want to register this kind of job. No, just say, hey, I would like to run this kind of job. Who can provide that for me? Oh, you have a GPU? Great, I'll send that over to you. This compute substrate has more than 4 parts, but the 4 that we're really going to think about here are scheduling, execution, verification, and reuse. I think it's uncontroversial to say that WebAssembly is eating the world. So WebAssembly, for those not in the know, is ironically neither web nor assembly. It is a common execution engine that exists in all browsers and also runs on desktop and mobile, where you can write code in any of 40+ languages, and it'll compile into this same virtual machine and be able to run anywhere. WebAssembly itself isn't deterministic. It has one little corner where it isn't, but you can enable a flag and make that go away. There's a small performance penalty, but you can make that case go away and get completely deterministic computation. So if I run something or you run something, we'll get the same result every time, which is the final part of this stack that we talked about right off the top. If we have auth data and compute everywhere, with things like UCAN and IPFS and the web native file system, we can compose them together with a bit of glue, or maybe a lot of glue, and get something like the Interplanetary virtual machine, which is what we've been working on at Fission. The basis of this is an idea that goes at least back to the 50s, if not earlier, called code as data. So if I have arguments and some WebAssembly, literally the binary, and I content address them, and the WebAssembly itself is just built on just regular standards. There's nothing special here, right? It uses, in our case, the WebAssembly component model, which is out of the Bytecode Alliance. We can combine them as a task, and then also attach a little bit of scheduling information to say like, well, I want this to run, up to, this much timeout, et cetera. We get something that looks a little bit like a closure, right? It looks a little bit like this kind of code, right? Here's a function that will, when it's invoked, cause an alert box to pop up. But it doesn't do it right now, right? It's just a description format that we can move around as data. I can pass this reference around, right? Because I can content address all of this. It's just data. I can pass this around and nothing happens until I say, hey, actually go and execute this thing, and then I get the pop-up. And when it actually runs, we get a new structure that points at the task, and we call this a receipt. And it contains a little bit of metadata and trace, as well as the pure values that have come out. So if I'm doing addition, 1 + 1, it'll give me back 2, and any effects, anything else that I want to on-queue into the system afterwards. One of the major advantages of this, of having it be ubiquitous and able to run anywhere, is that we get very, very high availability. There's a term, embarrassingly parallel. This becomes embarrassingly available. Systems try to run with replication so that they get high availability, so that you can't take the system down. Joe Armstrong, one of the creators of Erlang, said there's no such thing as 100% uptime. Right? You can have cosmic rays or an earthquake, or the network goes down, somebody cuts the underwater cable, and it's no longer available for some period of time, right? Amazon goes down, and they're brilliant engineers, right? But if we can replicate this, because anybody can run the computation, we get very, very high availability, and you can make a request to any of these providers. You have options. You have choice. And it scales up. More people using it, more people that can also plug in and run jobs as well. This is run by the community, for people. And if we take any section of this and add up the availability inside there, so these are not super high availability numbers, right? We have 99.0% availability on one of these. But if you combine them and do the simple math to find out how available this is now, just these 3 are now 11 nines of uptime, which is pretty good for most SLAs. So in aggregate, if enough people run such a system, we have essentially approaching infinity nines. We have incredible availability across the system. There's a downside. You need to actually find somebody to run the compute for you. So most of the time, that's yourself for most jobs. But if you need to have access to, say, a GPU and you're on your phone and it doesn't have enough power for something, you come online and you say, hey, I want to run this job represented by this gear. And you have a service provider that says, hey, I can do all of these things. You need to get routed through some common layer. In the current implementation, we do this over a pub sub system called Gossip Sub. But you can also imagine putting this on a DHT so that you can advertise, hey, these are the things that I can do. Route to me, please. There's also a concept that we're not going to delve too deeply into in this discussion called affinities. So to say, hey, I have a GPU and capacity to run right now. I'm a reputable source. I'm really close to this petabyte of data that you want to operate on. You should send the job to me instead of to somebody else. Instead of just sending individual jobs at a time, which is totally fine, but means that you're always waiting for a response back continuously, we do this thing called a distributed invocation with promises, sometimes called promise pipelining, that looks a little bit like data flow, right? Where we can take the output of one thing and before it finishes say, hey, when that's done, run this next thing as well. And we can send them together or we can send them over time. It doesn't really matter. And they can chain together into these graphs of computation that don't even necessarily have to come from the same user. They can come from multiple requests, multiple people reusing the same results. So we can take this graph and push it to a single machine, but we're not giving, there's nothing here about the location of where things run. We've taken that decision away from the programmer and said, at a high level, what kind of thing do you want to run? And we let them lay it out like this. And then the system looks at it and goes, oh, OK, I need to schedule that for efficiency reasons on these two separate machines. So Alice will run these first two, and Bob will run these other two, even though it has to make two requests to get these values out of the initial computations. So as we're running jobs, with WebAssembly, it's actually quite low level. You only work with linear memory. And you want to pipe that automatically through. But you don't want to send just raw bytes around on the network, right? You want to have a little bit more structure. You want to have somebody sign, like, yep, I ran this thing. I certify that I actually produced it. So we do this pipe, where at the level of WebAssembly, the components stack together and run efficiently through. And in an async process, we pipe out, hey, generate a receipt for me. And that goes into a nice readable JSON document off to the side. And the advantage of this is now I never have to run that step again. It's deterministic. If I run it now or in a week, it's the same value. So if I have that same argument again in one of these chains, I can skip it and take the value out of that receipt and say, yep, pretend I ran this, put that value in here, and continue. And we can collect up these receipts. This is memoization at global scale. Ryan, our head of design at Vision, has called this run once and never again. An unexpected thing that comes out of this, out of input addressing, where instead of it being a hash of the content, it's a hash of the inputs to the cached output on the network, is we get a reverse lookup table. If you run AI tagging or moderation over some data, which is a pretty heavy process, you can cache that and say, if I run this model over this data, what are the tags that it'll generate? And I never have to run that again, as long as I trust the source. We can do all of the UCAN or capabilities signature checking as well. They produce these chained certificates that cache really nicely. So you can actually use this same table to go and cache, was that thing valid? Yes, no. Last week, Zishan did a demo of this system. So here's the demo. Basically, what's going to happen is it's a pipeline of images that are being, of an image rather, sorry, that's being transformed. we're going to simulate a crash halfway through and resume, and then also do a variant reusing parts of the computation. So here's our nice cat on a space keyboard pic. We're going to show a little bit of the code. So it's just regular JSON with some content addresses for the WebAssembly and passing arguments to it. So these are the two functions that we're going to run. We're going to do a crop, rotate, and blur to start. And this is sending it off. It's not running inside the browser. It's actually going out to a remote process. And it takes a little bit of time to run the crop and a little bit of time to run the rotate. And here's Zishan simulating a crash by exiting the server. And the blur will time out. Okay, so we're going to go back, start up the server again, and start it again. But we've already cached the first two, so we never have to run those again. And we get the blurred photo at the end. So great. And workflow 2 does the same, but it's going to grayscale at the end. We don't have to do all that work again. We can just pull them out of the cache and get a grayscale at the bottom. And so we can do this across providers. Today, it's just point-to-point. It's actually relatively early work. It's about 4 months, I guess, in, but actually making pretty good progress so far. The upshot of this is that we can think about parallelization and efficiency from a new angle. So obviously, as you add more machines, you want to get linear scaling. You want to have it be, 2 machines will be twice as fast, 10 machines will be 10 times as fast. And in practice, that's not what happens, right? You need a little bit of coordination, called Amdahl's law, where the jobs need to synchronize and they need to check in with each other. Hey, I'm waiting for this thing. It's not done yet. I'm going to sit idle. All of this stuff. So it actually kind of tapers off a little bit. And in practice, there's a tipping point where it becomes less efficient because the overhead is so high. So I'm not sure if any of you have been in a team where the team then scales up really, really high, and you have all of this overhead suddenly. You have to have all of these meetings. It feels like you're getting nothing done. Same thing happens to computers, right? You have incoherence, data contention, you're waiting for things, you have to coordinate, check that you have locks, etc. But because we have this memoization, we can actually do better than linear on popular content. So this isn't on everything. This isn't on the first run. You pay a penalty the first time it runs, but after that point, you can pull it out of the network. And this isn't a completely new idea, right? This is how BitTorrent works. You can say, hey, how many providers do you have? The more providers, the faster it'll download. Great. Usually this is the point where people say, okay, that's great, but I have to trust everybody. And that's a trade-off you can make. You can say, I'm going to go to this specific centralized cloud in this bottom right corner. This is called Juan's Triangle, named after Juan Benet, the founder of Protocol Labs, who do IPFS. So you can go and say, I know exactly where I need to send this process. I'm not going to handle any of the abstraction. I'm going to just send it over to that specific server and it'll be really fast. And I trust them, so I don't have to do any verification. But if you're going into this commons network, where you may not trust everybody, you have a slider, right? The first one that we're starting with is called optimistic verification. It's very easy to think about. You run some computation. At the end, you get a receipt. But you run it on multiple machines. You scale that out to some scaling factor. It's entirely up to the user. And you then check, did you get the same thing? These are deterministic jobs. I should get the same thing back. If they don't, then you take the step that disagreed, and you run that one step on a often slower but trusted machine, and slash, reduce the reputation or take some escrowed cache from that one service provider. There are very cool but much slower solutions as well, like zero-knowledge proofs, where you can run on a single machine and get a cryptographic proof that it was run correctly. That's getting faster. It's practical for some things today, but probably needs a few more years before it's really useful at massive scale. So let's talk more about safety. This idea of pure functions and impure effects gets talked about a lot, especially in the functional programming world. The difference is that a pure function is just data. So it's 1 + 1 = 2. And an effect goes out to the rest of the world and either reads something from, let's say, DNS, or writes something to something that's outside of just what's captured in your function. So I can take an input to output, and this is always deterministic, and this works really easily. But effects kind of stick off to the side, right? So I can do a read or a write. And there's a little bit more to it in our case because we're distributed. But fundamentally, these can exist at any point. So how do we interact with the outside world, right? Pure computation is totally useful, but sometimes I need to send an email. Sometimes I need to read the latest value from the database. When we send jobs out, you can think of this as providers. The lower you are on this stack, the more providers can send this to can handle this for you. With a pure function, anybody can do it. I can run it locally. It's totally fine. With queries, or things that are broadly in the query realm, I send a job out, and I read it back in, and I attest to, when I did that read, when I went to example.com, I got this value. Here's some information from the TLS request, and I'm going to write that back into the stream as now pure data. Anybody can now reuse this as if it's pure value. They can say, hey, who's looked at example.com? Give me what you saw for that. I don't actually want to make the request out to the main network. If they got something that was wrong, or they want to do something like check that value, compute over it, and now write back, but only if things haven't changed, so to actually do a transaction, that's actually fine. It was just a read. We can roll back over that and try again. It's completely non-destructive. It's totally fine. The hard one is when you have mutations, when you want to send an email, when you want exact once effects, right? So I want to send an email, post a message to Mastodon, something like that, where it can't be done 6 times because people will find that strange. So you get a lock on the process, you actually run the thing, you get the receipt back, and you unlock it. You can't roll back over this one because it's gone and it's changed to the outside world, right? So these have to be handled much more strictly. And while the pure functions can be done in this very, very disorderly way, right? We can run them anywhere, we can retry them, we can pull them out of previous runs, and just make them as fast as possible. Anything with mutation will be slower in the way that making requests today is a little bit slower, because you have to go to a specific place with a specific source and actually run it there. I mentioned that it's not quite query and commands. There's 3 properties that we care about: determinism, idempotency, so if I run something multiple times, I get the same value, and mutation. We can build up these graphs that I was talking about before at interleave queries and computation, as long as the mutation is at the bottom. If we interleave mutation as well, we can end up with partial failure. So if this first top left mutation fails, if that runs and then the second one fails, how do I roll back over that mutation, right? It's possible. There are systems that do this, but it's a lot harder, right? The good news is that there's been work on this in the past few years. This is a lovely paper, highly recommend, Ambrosia, that says that if we take the lessons from databases, which we have half a century of experience with, we can completely isolate developers from the possibility of failure, right? Database transactions are awesome. What if all computation worked like that? Here's the simplified layout, so it's not a specific tree. We can have optionally queries and optionally some computation, and these can loop back and forth. And as long as the scary, horrible mutation at the end there's just one, and it's at the very, very end, we have a totally safe system. We can always retry these first parts as long as that mutation is the one at the end. And not only that, because we, the system, not the developer, have control over when things run, they don't have control over do things in sequence. They just get the data dependencies between them. We can say, OK, This is what you gave us as dependencies in the layout. I'm going to put the mutation to the very, very end. I'm going to wait for everything else to succeed, and then I'll do the mutation, which gives us safety. So, to wrap up, what we're talking about is related to open source. Open source originally was called commons-based peer production, which is a bit of a mouthful. The definition is lots of people work on it, everyone benefits from it, and people can build on it, even in a revenue-generating fashion. And we're saying it's time to update this for infrastructure. Everyone can work on it, you can benefit from it, you can build on it, and it is owned and operated by everyone. By participating, even if you're being competitive, you're strengthening the network for everyone. This is how the bottom layers of the internet work, and it has this virtuous cycle. We're building a bunch of specs to make this work. If you don't like the specific way that we're doing things, please reuse another part of it. We have auth with UCAN. I didn't talk about IPLD WIT, but this is our ABI, and varsig, which is a generic signature format. We have invocations built on top of UCAN and pipelines. We have an IPVM task spec and workflows. These are all joint work with various other groups, including Daghouse, Bacalhau, Ceramic, and a few others, Protocol Labs. And we will be working on consumable channels, doing things like fuel or payments over time for those that need them. Join us if you want to build together. Here is the GitHub working group and our community calls right there. Thank you.
Hi, Eugene. Fantastic talk, very inspiring.
Thanks.
I have a ton of questions, but I'll just keep it to one. Okay. What are the differences between the IPVM and the FVM, specifically when it comes to incentivization?
When it comes to, sorry?
Incentivization.
Ah, I see. So Filecoin has an execution engine called the FVM, right? It's also WebAssembly based, but it's deeply integrated with Filecoin. One way of thinking about IPVM is it's the equivalent for IPFS. So Filecoin is a blockchain. It runs, sequentially. Has all of the normal, blockchain-y trade-offs. IPFS is this open network that anyone can run, including for free, including completely locally for themselves. It doesn't require global consensus. And so the same thing for IPVM. It's the execution engine for IPFS and systems like it. There's no baked-in incentivization layer. We're leaving that open so that people can say, and this is part of the channels, to say, okay, I'm going to do this totally for free for anybody and be a volunteer, or I want you to pay me on a payment channel, and you can do both.
Over here. Hi, Discordian. Perhaps a very similar question. What would you say are the key differences between IPVM and Bacalhau?
Yeah, Bacalhau, so we work with them on this work. They are adopting these standards. So in some ways, they are an IPVM. They are much more focused on non-deterministic jobs like Docker containers and data science. We're much more interested in doing deterministic things everywhere, including in the browser, and making it this universal spot, universal place to do computation. But because we're adopting the same standards, we should be able to. We haven't actually done the integration yet. They're getting prepared for their own conference in a couple of weeks, and so we'll do the integration after that. We'll be able to call into their system for Docker jobs, and they'll be able to call into us for deterministic compute.
When can I start using this?
So we have some very, very early code up. It works. I wouldn't put it in production yet. I don't know, Zishan, how fast do you think you can build it?
Any day now.
It's at the point where you can play around with it. The demo that I showed is real. You can actually click through that. There aren't people actually running this on the network yet. our hope is that by sort of end of year, we'll have something that people can just say, hey, I want this thing run, and it'll just go off and hit the network, and you'll get results back.
Super cool talk. Really excited about the whole ecosystem. Just zeroing in on one little offhand comment that I was really interested in. What's the state of TLS notary and recording TLS sessions and then reusing those as proofs? Because that seems really significant. Or what are the constraints around that?
Yeah. So this is there's a paper called Deco. It doesn't require the server to change at all. The client needs to run a second, or it needs to coordinate with a second party where they basically join their keys before they make the request, and then you have the second attestation that this from a third party that you got back what you claim you got back. The paper's great. Would recommend. I'm not aware of it being put into practice other than we're looking at this actually for a couple of our systems. Blaine on the Fission team is building a name system, thinking of it like a superset of DNS that also runs in this self-certifying way. That will also probably use something like Deco, but it also gives you this ability to, instead of just saying yeah, totally trust me, this is what I got from the server, you can also get secondary attestations that in that specific session, this is what happened.
Other questions? Cool. Thank you, Brooklyn.
Great, thank you.